14. This is 14.7. We're working on the Jacobian. We looked at the 2D version yesterday. 3D version is like the 2D version. The 2D version was XU, XV, YU, YV, and we did the determinant. The Jacobian for the 3D is the larger one. We do, as a note, take the absolute value when you're done with any of these. It's a little, it looks wonky to write it like that. It looks funny to me to put absolute value signs around it. But you'll see this, and what they're saying is take the absolute value of the determinant.
The sun's coming out.
So, we got some functions up here. Let's figure out what our matrix looks like. X, derivative of x with respect to u is, what we got? 1 minus v. Derivative of x with respect to v is negative u. And with w, it's 0. Y is the fun one. Look at this bad boy. We got v minus vw. And then when we do v, we've got u minus uw. And when we do dy dw, we get negative uv. And z just leaves the other two letters. So u leaves vw, dv leaves uw, and dw leaves uv. Well, this looks like it's going to be a clusterfuck. That's the official terminology for it. So we have the I component will be 1 minus v.
LU. That was free LU. STER. Based on what?
Mr. Jones, why are you putting an I at the beginning?
It's the I component.
But we don't have an I component. It would be an I component if there was an IJK at the top of the matrix.
You're right. Testing you. That's what I'm doing. Yeah, that's it.
That one?
And then minus a negative u.
I'm at a V. Right,
Or is it?
right here.
Or is it one?
We've got v minus vw times uv
I'm doing it right.
minus u negative uv times vw.
As you can see, this is what's called acute yes.
And that's how we end up doing the Jacobian. Does this clean up at all? It might. So do the algebra and clean it up for actual use. This was just an example.
No, this is just the second one, so it's just negative. It's the
Oh,
same
I
as the
see.
regular
I
method.
see, I see.
There's just no third one because everything's just multiplied by zero.
Here I was just doing it to set up, show you how to do the Jacobian. I've got some actual examples where we'll do the integrals with it. And this is one I didn't want to do, but it's good practice.
It's almost real.
What, Eric?
Oh, that turns into zero? Yeah.
I bet it does. I could just see, nah, zero. No, I can't see it going to 0. That would surprise me. Maybe 1. Are you sure it goes to 0?
I'm checking this work right now. He's checking it. Oh, that's
Did I get this from the book? I think I did.
Your thing looks right. I mean,
It look like you can make things 0.
This is problem number 10.
Just look up there.
It equals u squared v.
Would say,
If you clean this up, it's u squared v.
let's get it on how did that seem?
I'm looking for it.
That was the point of this.
What's your 1.6 ratio? What do you treat those?
We're not gonna clean it up though. We're gonna move on.
You fine doing it?
That's way too much waste of time doing.
Like,
Yes.
cover the bottom one and you.
Well, what you do,
Well
you
done.
just cover this row. And it's this, for mine, this. that
That's
row.
right. That's what you.
Let's start with
You
the
know,
simple one.
I take the up here, but I take the up.
Another idea.
Wait, come back.
Okay, so the way we use Jacobians in the real world
And then.
and why we use Jacobians in the real world. If I graph y equals negative x, what do I got? I really hate competing with people.
Cover the side and do this times that times that, times all that.
You say you hate what?
Competing with people to talk. It's annoying as fuck.
Yeah, especially when they just like talk over you while you're talking.
Yeah, I've tried, like, we've got, this is our last lecture before review, before the test. Let's get this shit done. I want to make sure we get it done. So this is a fucked up region. I don't like it. No matter how I do it, no matter how I cut it, it's just not going to be pretty.
Let's see.
So this is a good opportunity to say, let's use the Jacobian. And I've got this line is y equals, we've got y equals, these two lines right here is y equals negative x and y equals negative x plus 1. And I'm eyeballing this and going, what does this look like? This is x squared minus y squared. I could rewrite as x plus y, x minus y. Maybe I should try to write these like those. And that way we have an easy U sub and a V sub. So if I add x to both sides, I could get x plus y equals 0 and x plus y equals 1. So I could say u equals x plus y. And then I'm going from u equals 0 to u equals 1. I like that. Can I do the same thing with the x minus y? So I've got y equals x and y equals x plus 2. I can. I want to move the x to the left, but that's not going to get me where I want to go. Let's move the y's to the right. I've got 0 equals x minus y. I'll subtract 2 to the left and the y over to the right. And now I've got these. I could say v equals x minus y. And so v goes from 0 to and there's a negative 2.
There's 2 lines.
So those will be my regions. And if I change this, that would change the integral on the inside. Let's see if I do v and then u. I don't know which one's going to be the better one to do first. Negative 2 to 0 and then 0 to 1. This would make this whole thing uv. The question is, what does dA become?
So those are the givens, yes. So that graph right there is a representation of the area he's supposed to integrate over. What
I'm
he's
going to
doing
pause
is
and let that sink
find
in a
a
little
way
bit. Let's catch up.
to Find a way to simplify it so he doesn't have to deal with this. That's what the Jacobian is.
So the square looks all fucked up. I don't like this square. It's not even a square, it's a diamond. weird limits. Like if I go vertically, it's got this. Eh, not a big fan.
What input in to try to get to that point.
So I let the equations kind of guide my choice.
It is very stupid.
Jones,
Yeah.
can you go back through with what you got and how you got it?
Yeah. So I drew the picture and go, this picture's fucked up. I think we could all agree this picture's kind of fucked up to do. We got 3 regions going vertically. I'd have to look to see where these line up going left and right, but I suspect it's not equal. So I've got these equations right here. And it would sure be nice if I could map the equations so that it makes an easy region. And I looked at these and then I rewrote x squared minus y squared as x plus y, x minus y. And I go, can I make these match that? If I can, things get pretty easy. Can I produce an x plus y or an x minus y? Well, starting with this, it's kind of easy to produce an x plus y. I add x's to both sides. I get x plus y equals 0. And I do the same here, and I get x plus y equals 1. So if I use u equals x plus y, I now go u equals 0, u equals 1. And on a UV graph, I've got nice simple limits of integration. And that is taking the y equals negative x line, which is that line right there. Well, that line right there, and the negative x plus 1 line, which is that line right there. So I've kind of mapped those 2 fucked up lines into a nice rectangular region. And it matched well with this. And oftentimes, well, in problems like this, and on the test, it's kind of catered this way, even by me. There is some catering. Maybe not on the hard mode test. Maybe it'll be just all fucked up every which way. Then I'm like, well, can I do the other one? Can I get the x minus y map? If I can, this turns into an easy problem. If this is u and this is v, I'm off screen. If this is u and this is v, I just have this integral right here. So can I make it x minus y? I've already dealt with the top line. I've dealt with those. So I'm looking at y equals x and y equals x plus 2. If I want to get x minus y, I got to subtract it over. So I did, and then in this one, I moved the negative or 2 over to the left. Through subtraction, you can't just move them, mind you. As much as some of you have tried to do on your tests, it doesn't work like that.
So basically, we just find a way to rotate the coordinates.
Effectively, that's what we've done. In this case, it's not always, this we've made it nice rectangular. You can't always make it nice and rectangular, but sometimes you can. In this case, you can. Oftentimes, you will see things that are, if you look at the function that you're integrating, and you look at the equations you're dealing with, like we're going to do a couple more, they kind of guide your choice. Like what you has guide your choice. So let's at least finish setting up this integral, even if we don't solve it. Let's finish setting it up. We still need dA. So dA is going to come from the Jacobian. We need to shift dA over to Jacobian of UV with du dv. So to do the Jacobian, I need x and I need dx du. I need x's in terms of u's and v's and y's in terms of u's and v's. So right now I've got u equals x plus y, v equals x minus y. If I add these up, I get u plus v equals 2x. So I could say x is 1/2 of u plus v.
And because of that, we found that u is equal to 1.
And then I could also do,
And then b, that b would be -2. And b would also be 0.
if I subtract minus v, the x's go away and I get 2y.
And,
So y is 1/2 u minus v.
So it's not a good.
Can't follow his word. Like, it took me like the longest time just to figure out that this y equals -x, same here, you take the x over. And they do the same thing here. That's these two.
Yeah, so he's.
Right.
So these are the two things I'm working with.
Okay, perfect.
So I need xu, xv, yu, yv. One half, -1/2, -1/2.
Why do you like Cambridge format?
And remember, we're taking the absolute value of this.
Yeah.
That's gonna equal 1/2.
You got a question in the back?
Yeah,
So where did the 1/2 come from? Like, I know we found 2x and 2y, but why did we change it to what? Oh, wait.
I
Oh,
divided
never
by
mind.
2.
Yeah, okay, yeah.
I solved for x.
Just check mine. V minus V over there.
Right over here. Or the top. Right here. Oh, to get this? Oh, because the input is.
Oh, no, you inputted something for X, and you're saying.
So the setup would be, I've got v going from -2 to 0, u going from 0 to 1. I had x plus y, x minus y is uv. My Jacobian, the dA right here, is 1/2 du dv. That's my dA. So it's the Jacobian. So I would probably put the 1/2 out front.
That's what I was thinking. I thought I assumed it was wrong. I should just ask questions.
And we could solve, but we're not going to. I'd rather set up the rest of the problem. The hard part of this shit is the setup, right? This integral is easy to solve once we have it. So I think if we do more problems working on setting them up in class, it's more beneficial to you. So I let that, I did the graph to see how it looked, if I can. Because it didn't jump out at me right away what I needed to do. And then I let the problem, like the function and my boundaries kind of guide me and go, what could I plug in here?
How they change me into GX and DY. But they still, because what he did is he still has to put the X and DY to be in here, the DV. That would be D. That's
Let's see, what one do I want to do next? Let's see this one next. You guys ready for the next part? Okay, so we're gonna integrate x squared over the region 9x squared plus 4y squared plus z squared is less than or equal to 36. This is an ellipsoid, which is gonna give me shitty boundary conditions. I don't even want to write the equations for the boundary conditions in an ellipsoid. I think it would take me far too long to set up. So let's at least make it look a little bit more like an ellipsoid by dividing by 36. So this becomes x squared over 4 plus y squared over 9 plus z squared over 36 is less than or equal to 1. And those denominators are all perfect squares. I could write this as x over 2 squared plus y over 3 squared plus z over 6 squared equals 1. Okay, so any ideas what we could do from here? Are there any substitutions I could make that would make this much easier to deal with?
X equal to U, Y equals 3Y, 3V, Z equals 6W. Remember?
I would just kind of substitute the variables themselves.
If you make this u squared plus v squared plus w squared, it's kind of easy, right? It's a sphere. But that means I gotta set u equal to x over 2, v equal to y over 3, and w equal to z over 6.
Right.
So here I can go into spherical, and the boundary conditions are really easy in spherical. Really easy. We've got 0 to 2 pi for theta. It's a full circle. So 0 to phi to pi, and then rho goes from 0 to 1. The boundary conditions for spherical are easy. The only thing that's going to do is going to force me to introduce the Jacobian to switch from dv to spherical.
You feel like rho squared. Rho is equal to 1.
So that means to get the Jacobian, I need to write these in terms of x, y, and z. So I've got x equals 2u, y equals 3v, w equals 6z.
Z equals 6W.
Yeah, I said that backwards. Thank you.
This.
So I need to do xu, xv, xw, and then do the same thing for y and z. So dx du, partial of x with respect to u is just 2. And for the other variables, it's 0. And you can see this ends up being a pretty easy matrix.
Okay, he just did.
And the determinant of a diagonal matrix is the product of the diagonals.
This makes way more sense.
And he does get it. Yeah. Oh, sure. He just forgets a little bit. Okay. I'll check it out.
No, it just makes it go. Guess this one just works out well. Product of diagonals.
Products and value. I love it. Oh, the determinant.
So which was the name?
Yeah, no, like definition.
Yeah. And wait, what about the other ones? What's that? How's that?
This side. That's why I said you did the word.
So by switching over, what do we have? We've got G 36 x squared. X is actually 2u, so
The
times
other one,
4u squared.
Press the lever.
dv. And u is like x in our equations, in our spherical equations. So u is rho sine phi or sine theta. I'm sorry, cosine theta sine phi. It's like the x in spherical. We were doing u squared plus v squared plus w squared. Although I suppose we can choose u to be, well, no, it's u is the x. So there's no real shifting it around. So I don't know, what's 36 times 4? 72, 144. Got a 144 out front. U squared is going to be rho squared cosine squared. That should be a phi. Sine squared phi. And then we're shifting to dv, so rho squared sine phi d rho d phi d theta. And then we have our intervals in spherical.
So, Mr. Jones, why is it that, where did you come to the assumption that you could assume that u is just about x instead of x over 2?
I didn't say u is x, is u is like x in the equation up here.
Yeah, you have a question, Jacob?
Yes.
I don't speak to you from over there.
Oh, you want to talk to me? Okay.
Because you're here, I don't know. So, yeah. Right. I can't get this. I don't even know. My brain.
Okay, you're not following the matrix?
I can do this without the third row. You use
Oh.
that, and then
Well, it's the same thing. It's actually the same thing. It's just looking at it from a quantum perspective. Imagine this is your I, and this is your J, and this is your K. You're multiplying, because technically you're multiplying by I by a certain area. You're multiplying J by a certain bit, and you're multiplying K by a certain bit.
You can work out this cross product if you want. You will learn in learning algebra, if you've got zeros along everywhere else except the diagonal, the determinant is the diagonal, the product of the diagonal. I was speeding this up for presentations. You can go through and do this the regular way and still get 36. Just using some tools. Yeah,
Why is it 4u squared?
because x equals 2u and we're doing x squared. So the quantity 2u squared.
You're taking x to u and multiplying it by your two matrix of one. Then you have say your make sure you have second one negative. And it's with the difference of y, z, and z.
Yeah, I can't see that. This time the stage.
No. This times.
Let's see, which one do we want to do next?
Oh, hold on, that's what. Not so fast. It's the one, it's the same idea, it's just bring the row, it's everything.
Okay. Ready for another? Wait, Eric, you're still writing. Hold on, I'll probably be back up.
Sometimes. Without Eric ready.
Yeah.
That's it.
Yep, that's it.
Okay, when I'm ready.
Yeah. A little weird, like awkward matrices without the IJK first, but I'm sure if you get in the front.
Well, you're saying those are the ITKs, so multiply. You're saying those are the ITKs.
Essentially, yeah, but they're actual like values of something, and variables that you can multiply out.
I'm done.
That's just, they're just place
So
other.
those ITKs were actual values. I think, right?
So we want to find the volume of the region in the first
Yeah,
octet. So
they're actual. The IJK of the that comes with.
the first octet means everything's positive.
You can use this to make sense.
The hyperbolic equations, x, y equals 1, x, y equals 2, y is equals 1, y is equals 3, x equals 1, x equals 4. Now, just to picture so you can get a visual what it is. If I solve this for y, this is y equals 1 over x. We know what that shit looks like. That shit looks like that. Except with the z component, it's let's see, we got something like that, and it's making this curtain. That's the xy equals 1 curtain. Xy equals 2 curtain makes another curtain. And then the other 4 equations all make their own curtains. And so it traps this thing in a very weird looking shape that I don't think I can do by hand. But looking at it, I see I've got xy equals 1, xy equals 2. Then I've got a y equals 1, y equals 3, x equals 1, x equals 4. Which makes me go, I see 3 things that pair up. And maybe I'll make my variables those. So if I say u equals xy, then I've got u equals 1 and u equals 2. And if I say b equals yz, I've got b equals 1 and b equals 3 from my boundary conditions. If I say w equals xz, I've got w equals 1 and w equals 4. So I'm looking at, if I get rid of the picture of the boundary curtain, I'm letting what the ugliness of the equations guide me in my choices, because if I set it yet to this complex or this product of x and y, this becomes really easy. Now, the real difficulty here is writing these. If I want to do this, I need to do dx, dy, dz over du, v, and w, which means I need to write these as x, y, and z. So, like, if I try to get my x's together, let's look at how I would get my x's together. If I wanted to get my x's together, I could do something like, let's try u plus w, and I would have xy plus xz, or xz, sorry. And that's going to give me x times y plus z. I don't know that this is helpful here, because I don't have a y plus z going on anywhere else. So I think I went up the wrong tree. I don't think I chose a good way to combine this. Let's try something else. Adding them together doesn't work. Maybe multiplying them. If I do u times w, I could put them together and I would have x squared yz.
I just picked
He might-
if I pick the wrong one, I just fail automatically.
Okay, well, it doesn't mean just because.
Now,
you
can I
pick
get
the-
x squared by
fail,
itself
you
here?
integrate it correctly, it won't be a problem.
I need to get rid of yz, and I have
Well,
something that's
another
yz.
country entirely.
If I divide by b, I could get this down to x squared. So x squared is uw over v. And if I take the square root, I can get x. And I want just the positive version because x is greater than 0. So the addition thing, this didn't work. Blue didn't work. So I looked at other ways to get my x's together. Addition and multiplication are common ways of doing it. I'm guessing I can do something similar to get the rest. So let's check it out. If I wanted to get y, I could multiply u and v together. So u times v is x, y squared z. And so I need to get rid of the xz. Xz is w. So I get y squared equals uv over w. So y will be the square root of that. And then we do z. Z, I gotta multiply my z's together. So v times w, x, y, z squared. And if I want to get rid of the xy, I have a u, I'll divide by u. So z is going to be the square root of v times w over u. As you can imagine, this Jacobian is going to be ugly. Would you guys rather work through the Jacobian on this problem or look at setting up another problem in our last 10 minutes? Because at this point, we're just doing partial derivatives and doing the cross product.
Next.
Next, do the next problem. All right. I'll leave that up for another minute or two and take a look at the next one. I think this is a lot of grinding, some algebra and some calculus, but some easier calculus. Partial derivatives weren't that bad. I think the setup is really the hardest part. I may be alone in this.
Out of curiosity, because I'm sure your students are very worried. Are you gonna have to like figure out the substitution themselves, or are you gonna provide the substitution?
I know in the hard test, they have to figure it out themselves. I'm still deciding on the other one. I might give it to them. It might be obvious.
Are you sure it's gonna be obvious enough? You know this class pretty well, don't you?
I think if you're paying attention and following along with what we've done in lecture notes and practice it later, you might have it all right. Let's see. Did I think let me look at what I made them test yet. You guys can't see that, so let me go look. All you can see.
Okay, Carlos.
It's like the easy one. And there you go.
Oh,
I'm
wow.
deliberately picking hard problems for class.
Yeah, I would assume so. Mr. Jones, this is an interesting question.
I'm just gonna take a hard
Don't punish me, don't respond.
It's a magic keyword.
I think I didn't give it to you, but I think it's pretty fucking obvious.
Is called
Even is it 70?
Out.
All right, so let's look at the one more problem while we got some hours to burn.
just in case.
So it's like,
Give out.
that's why I have it, because
So x squared minus y squared are hyperbolas. And x squared plus y squared are circles. And so let's maybe focus on the first quadrant. Let's see, x squared is positive, so these are going to open like that. So maybe let's just go with the first quadrant. Well, we're not actually doing the integrals. We're doing the setup right now. So the problem, we could decide if we wanted to actually integrate it out, what we would do. The setup here, do you guys have any ideas of what we could use for u and v?
Not really.
Is anything repeating?
X plus one. No, not really.
You're plus.
Yeah, well, that's why.
It's gonna jeopardize my business.
That's why or that's.
That's a 4.
This is a 4 right here. This is a 9.
Yeah, physics taking so much resource.
And that's a 1.
So like if you're looking for an x minus y or x plus, this doesn't, the problem here is this does not factor, right? X squared plus y squared doesn't factor
No, it doesn't.
without imaginary components. So why don't we just let that equal one of our variables? Let's say that equals u. So then I've got u equals 9 and u equals 16. And u equals x squared plus y squared. That's like this generates the easiest boundary conditions. If I make this u and maybe make these v, I say v equals x squared minus y squared. Then I'm going from v equals 1 to v equals 4. Now this may not work, but it's at least worth a check because now my integral is really going to be super easy. The integrating will be easy for the boundary conditions if this setup works. There's no guarantee it's a good choice, but it's always worth a check. It generates the simplest boundary conditions. So can I write u and v, or x in terms of u and v, and y in terms of u and v? So how do I get x equals xuv, y equals yuv? Because I need that for my Jacobian. I need these for my Jacobian.
Oh, well.
So I like that I see a plus y squared and a minus y squared, because if I add them together, it means I get rid of y squareds. So I've got u plus v equals 2x squared. And if I divide by 2, I've got x squared equals 1/2 uv, u plus v. And so I could do x equals the square root of that. Now the Jacobian might be ugly, but at least it's just a one-step ugliness. even figuring out how to set up these boundary conditions and figure out how to integrate and leaving them in terms of X and Y, I think is going to be worse. Also, by this logic, if I subtract X squared, or if I subtract V from U, so I'll rewrite it. And if I do subtraction, U minus V, I have X squared minus X squared is 0. Y squared minus a negative Y squared is plus 2Y squared. So divide by 2. And then take the square root.
Let's do. Let's do. Here, BBC on there.
So we could do our matrix dx xu, partial of x with respect to u, partial of x with respect to b, partial of y with respect to u, and partial of y with respect to b.
He did the same thing again. So. It's not going to be an easy one.
You could also try, and I don't know which one's going to be better. You could also try doing like u equals x squared and v equals y squared. You could try that. So we would have u minus v equals 1, u minus v equals 2.
Finding your.
But I don't know if I like that. So maybe not. Maybe I wouldn't do that. It still makes wonky boundary conditions.
It's not going to be boiled down to first finding your fusion steps. Figuring out solving for x and y, and then implementing the Jacobian, and then taking all that and implement it into your final integral. It's not always going to look pretty.
So when you get down to the final integral, we've got v will go from 1 to 4, u will go from 9 to 16. We will have our xy, which is ugly. 1/2 u minus v times 1/2 u plus v. That's ugly. I don't know that I like it. Actually, that goes together. That makes a 1/2 squared u squared minus v squared. So maybe that's not too bad. But then we have the Jacobian part. I don't know what the Jacobian looks like. And with it being 9 o'clock, we don't have time to figure it out. But it's the derivative, it's the partial derivatives with these in that matrix and do the determinant.
I'll work on that.
I will upload the practice exam right after this so you can see what kind of problem we're doing for the Jacobian section.
So we're just rewriting the equation. We go to 115 for. Problem. I'm just like, I don't like the way the miracle looks. So I just write it to look better.
Oh, yeah, right now, yeah, what, bring on.
Yeah. You do that.
I'll be holding my regular SI hours today from 1 to 3 p.m. And Friday has changed spots. We're gonna be in John Muir 107 from 4 to 5 p.m. Hey, have a good day.
You guys have a good day too.
Ooh. Well, no one ever said that the Jacobian would always look pretty. That's for sure. I left it out.
Good as Friday.
Yeah.
Have a good day. It's not too bad once you start recognizing you got to look for patterns in the equations and stuff.
Yeah.
And just keeping in mind that you're trying to generate something simple for boundary conditions.
Yeah. Yeah.
Can we just do Jacobian on all the questions on the exam to get the integral to look the way we want it to look?
I mean, in a way, you could technically
You could
do
say-
Jacobian on doing
If you
cylindrical
wanted
curves.
to spend far too much time on problems to do it, yeah, you could.
Maybe I'll get the extra time and then I'll just do the Jacobian on every problem.
Hey, you'll get something.
I'll see you guys later.
Yeah.